Welcome back. And I bought this motor plus gearbox and encoder as a different one from the Fit0177. This one is the Fit0277 from DFRobot. It's a really nice looking device actually. There's the encoder on the end, there's a gearbox here, and the motor at the front. This I put on, this is just a load, and it's a 12 volt device, 146 RPM, a bit faster than the previous one I had. It's got 13 pulses per revolution for the encoder, 663 pulses per rev with the gearbox connected, and it's got a two-phase encoder, which means it's a quad thing, so it gives you out the, so I can connect it almost directly into what I've got already. So it comes with some connecting cables, so it's this little board that you plug the things into, and I've connected my own set point to the control system, and I've got a 8-bridge off the shelf, myRio, and a 12 volt power supply, and I'm going to close the loop around it. I haven't spent a lot of time tuning the thing in, so to speak. When I say tuning, I really mean designing, but here's the program that I've used quite a lot. I don't expect anybody to follow this because it's kind of complicated. It's probably an example of how not to program in LabVIEW, because once you have these huge programs, it's difficult to see what's going on, and you should split it up into subs. But I have got a sub here for my PI part of the controller and my phase advance, which is all I really need. My PI and phase advance. Here's my PI. It's just formula nodes. I've discretized the formula and converted it into Z transforms. Same with the phase advance. Phase lead. There it is. It's just a formula, input and output. And I put a low pass filter on the output to stop any resonances. And I've got, what I've also done, which is quite interesting, is I'm storing the data from the position of the shaft and the set point, so I can see how good the tracking is. And I'm storing it just in arrays, so I've got, this is build arrays, and the array gets bigger and bigger. It's probably not brilliant, but you know, if you leave it on for too long, you'll run out of memory. So it builds up an array, and then once the program's, you then stop the program and then you plot it. I merged the two graphs, so I'm plotting here the set point, and this is the response. So I mean, if I go back here, I can put in an input. Let's just put a square wave in, for example, and let's measure the response, the input and the output. So there's my phase advance, and there's my PI, and they're in cascade. It's not PID, but I guess it's, if you do some maths, you can show it's very similar to PID, but it's not PID. So I'm going to run it. I might have to hold the motor because it's going to jump. Oh. So here's the motor. So it's a 1 hertz square wave software generated direct digital synthesis, if you want to know, and it's going in and feedback and so on. So I'll stop this, and then we'll have a look at the graph that's produced. So here we go. So we can see this. So there's this textbook stuff here. I'm going to zoom in on this. I'm just going to go to, say, time 2 seconds. Oops. And there you go. The red one is the input, and the white one is the response. You can see a tiny amount of overshoot. Now if you want a faster response than that, of course we can do it, but you'll pay for it. So you can increase the bandwidth. That'll give you faster response, but you may get more overshoot, and you'll have to do other things to dampen it. So yeah, you can play around with this as much as you like. Well, let's look at another type of input. Let's look at a ramping input, because this works as a speed controller. As a position controller, I can just put a ramp in and see what happens. So let's run it again, and oh, there it goes. Let's run it negative, sort of sticking there, positive. Stop it. It's just got these funny things on it, 0.5 to 1, just scaling it. You can see the set point and the output. You see how it's a classic type 2 system. It responds to a ramp. So I don't know what it's doing there. It's just sort of starting up, and then the output is an error, and then it goes back in and follows it, which is rather nice. So you see in textbooks. The other thing I can do is I can just follow an arbitrary input. So turn that back off again, turn that down, so it now works off my set point, which is a manual set point, which is this guy here. So I'm just going to turn it back and forward and do a few funny things. So it should record all this information and plot it like an oscilloscope. So stop it, and then you see it looks like an oscillation. That's just how I've been moving it back and forward, but we'll zoom in on it. Now these are waveform properties, so this is actual time. It's not just samples. This is time in seconds. So 2.5, that's 2 point, so going to 24, 2.5 seconds. This is difficult to do with one hand. 2.5. Alright, here we go. So do you see the red one again? It was hard to see because it's such good tracking. The red one is the input, the white one is the output, and you see it's kind of lost it there a little bit, then it's come back in again. The white one is the output, and it's moving back in again. So the setup for this motor is I've got a center frequency of the phase advance at 300 Hz. I'm not convinced I've got a 300 Hz bandwidth, so the board plot might not be actually crossing at 300, but might be less than that. And I've just got a PI set to 2 Hz low frequency cutoff, and a gain which I determined by a little bit of trial and error, and a span ratio of 15, and a filter cutoff, a low pass filter after that at 1 kHz. Now this is done by the FPGA, so this is the information for the set point and the speed and so on comes from the FPGA. I haven't used the real-time controller, although it uses the real-time controller and the FPGA. If I go to the Program Explorer, I can go FPGA target, which I've compiled before, and there's my servo thing, which I've used many times before. So there's code in there, all these parallel loops, because it's an FPGA, they're all running in parallel. So that's just for forward and reverse. So you know that the complement of one another, that goes high, that goes low. This loop here is the quad-detector detection. I didn't write this. This is a National Instruments one, but works really well. It tells me the position of the shaft in pulses. There's another one for the quad-detector, so they're the same, really, different ones. And that generates PWM. We've done that in another video. And this guy here does the speed. But I'm not really using the speed here. But you know, I've got a measure of the speed anyway. Okay, so there it is. That's the DFRobot. What is it? The Fit0277. Rather a nice motor, and it's useful for a lot of home robotics. Thank you very much.